Excuse me, sir. Sir, we can't hear your voice, sir.
Okay, it should be okay now. So, chapter 5 and chapter 4, a part of the chapter 4, chapter 5, chapter 6, and part of chapter 7, I'll be looking at, I'll be discussing with you. Then, Pasindu will take care from that point, and he will be looking at this moment distribution method, slope deflection method for frames after the 7th week. Your mid exam will be covering whatever we cover in the first 6 weeks. Okay, so let us start. So the first section we are going to cover is analysis of statically determinate beams. Sorry, frames. Already you know how to analyze the statically determinate beam. So it is same, like everything is going to be the same. So someone is waiting. So if we go to the chapter 4, okay, so we have come across ways of analyzing beams. So if we go to the frame problem, statically determinate frames, okay, shear and moment diagrams for frame. Now, frames are widely used in construction as well. So we see how to approach frame. Only difference we are going to see in frame problem is that take an example. Look at this. This is a worked example. I will explain you this and then we'll take a problem. So this is a frame. Okay, this is a frame because it's in a two-dimensional space and there's two elements connected using a rigid connection. That's forming a frame. So first thing we need to see in a frame problem whether it is statically determinate. So the check is similar to checking for a beam. So we need to see the support conditions, and if the number of reactions are equal to 3, then we can solve using standard equilibrium equations. If the support reactions are more than 3, then we can't solve using standard equilibrium equations. Then it will fall under the category called statically indeterminate structure. So R should be 3. R is equal to 3 means statically determinate and stable. R less than 3, statically determinate, unstable. R greater than 3, statically indeterminate and stable. So here what we need to look at is, say here we have a rigid connection. So if you take this, the simple analysis process is, first So first determine the support reaction. Okay, first determine the support reaction. Then what you need to do is, second, break the structure into components. Into elements. So here if you look at this, there is a beam element and there is a column element or inclined column. So we need to break at the joint. So we will have three elements, a column, you cut just before the joint, then you have the joint, then you have the beam just cut after the joint. Okay, so that is very important. The joint we need to separate that because we can't break at the joint because it is a rigid connection. So the rigid connection we will treat as a small element. So just before the joint, just after the joint. So the joint also will be in equilibrium. The structure is in equilibrium, the joint also in equilibrium. The column will be in equilibrium, inclined column in equilibrium, and the beam is in equilibrium. So that is the third step, second step, break the structure into elements. Third, solve. So once you break into this components or elements, now you will know, for example, if you take this inclined column, we know the reactions here. These reactions are known. Then you will have three unknowns here. Okay, you may have an axial force, you may have a shear force, and you will have a moment. Okay, all three will be there because it's a rigid section. So in a rigid section we can have three unknowns. It's like cutting a beam in the middle. So you can have an axial force, you can have a shear force, you can have a bending moment. So if you take that inclined column element, you have three unknowns to solve. So using standard equilibrium equations, we can solve three unknowns. Okay. So similarly, on the other side, again we have reactions known. Then we will have again shear force, axial force, and bending moment, and those three we can resolve. So now in the rigid element, there will be equal and opposite to these three actions on the other side. Equal and opposite of the actions or reactions on the beam will be there on the rigid element. So the rigid element will be preserved as a rigid joint and it will be in equilibrium. Okay, so that is the approach we will be adapting. So when we work out a problem, you will understand it more clearly. Okay. So let us take an example. So here you can see the support reactions are found first, then the section is divided into three elements and then solved and plotted shear force and bending moment diagram separately, and you can merge them to form the shear force and bending moment diagram for the frame. So once you plot the bending moment shear force diagram for the inclined column and the beam separately, you put together, and that's the bending moment and shear force diagram for the frame. So there. Now let us take this one. So the question is, draw the shear and moment diagram for each member of the frame. Members are pin connected at A, B, C. So A pin, B pin and C is a pin. Okay, A, B, C. Okay. So let us take this. Okay, so now A, B and C are pin connections. Okay. So now here we will have two reactions, and at C also we will have two reactions. Okay, so in any problem, the first step is drawing a free body diagram. So let us draw a free body diagram. Okay, so let us draw a free body diagram. Now since B is a pin connected connection, I can just disconnect that B. I don't need to treat it as a rigid element, rigid connection. So B is also a pin. Okay, so this is a different scenario where A, B, C are pin. Means if it is a pin, I can break at that point because there's no moment there. So pin means there will be vertical and horizontal reaction. So I have a flexibility to break at point B because it's a pin. So here I can mark a reaction RA. If it is a pin, I'll have RB, and I can have a horizontal reaction as well, HA and HB. And if I draw the inclined column, then equal and opposite will be there, HB and RB. Then we will have RC and HC. And there are two vertical forces here, 15 kilonewton and 10 kilonewton, and an increasing load for kilonewton per meter. Okay, so if I consider the so if we consider element AB, then if you balance vertically, you have RA plus RB minus 15 minus 10, 0. So RA plus RB is 25. If you balance horizontally, HA is equal to HB. We can't say it is 0. Okay, we can't say it is 0. But we can say it is equal to HB. Then we take a moment by A. So if you take moment by A, RB into the distance is 6 meters. Two meter, 2 meter, 2 meter. So RB into 6 minus 15 into 2 minus 10 into 4 is 0. Okay, so if you take moment by A, RB into 6 minus 15 into 2 minus 10 into 4 is equal to 0. Okay, so that gets us RB. So RB is equal to, this is 30, 40, 70 over 6. So 70 over 6 is 70 over 6. 11.67. So RA is 25 minus 11.67. That is equal to 13.33. Okay, so we have found the reaction RA and RB. Now we need to get the equilibrium of BC and again find the reaction RC. Okay, so if I consider element BC, so if we consider element BC, then if you balance vertically, you have RC minus RB, then there are some load acting. So at the moment for the support reactions I can take an equivalent point load, but when it comes to bending moment diagram and shear force diagram, I cannot take the equivalent point load, but I have to use the distributed load as it is. Otherwise you will get a completely scary bending moment and shear force diagram. So the equivalent is, now if you look at this load, so 4 kilonewton, so the area is half into 6 into 4, so that is 12 kilonewton. So the 12 kilonewton will be acting at 1/3 from the base. Okay, somewhere here, and this angle is 45 degrees. Okay, so it is making 45 degrees to the horizontal reaction. So it has two components. You can break that 12 into two components, horizontal and vertical. So that is the first thing we learned when we started structural analysis or engineering mechanics. The force can be divided into two components, or two components of the forces can be merged into one or equal in one reaction. So the 12 will have two components, 12 cos 45 and 12 sin 45. So the 12 sin 45 is going to be vertical, 12 cos 45 is horizontal. So RC minus RB minus 12 sin 45 is 0. Okay, so RC is 12 sin 45 is 12 into 1 over root 2 plus RB is, already we have found RB 11.67. So 12 over root 2, so that is 12 divided by root 2, 8.485 plus 13, 11.67. That is 20.16 or 155 kilonewton is RC. And if you balance horizontally, okay, if you balance horizontally, HB minus HC minus 12 cos 45 is 0. So HB minus HC is again 12 over 1 over root 2. So that is 8 point, how much? 8.485. 8.485. Now I can use my third equation to determine either HB or HC. Okay, so I can take moment by B and find HC, or I can take moment by C and find HB. So if I take the moment by B counterclockwise positive, so if I take moment by B, HB and RB will cancel off. So RC into the distance. So the distance here is, this is 6 meters, means the horizontal distance is, this distance is 6 cos 45. Okay, 6 cos 45. So HC into 6 cos 45, sorry, RC into 6 cos 45 counterclockwise, then 12 into 4 is clockwise. The distance here is 4 meters. 4 meters. So 12 into 4 is clockwise. Then HC into R 6 sine 45 is again clockwise. Okay. So RC into 6 cos 45 minus, so this is counterclockwise, RC into 6 cos 45 is going to be counterclockwise. Okay, so you have, if you take moment by that point P, RC counterclockwise, 12 clockwise, and HC clockwise. Okay. So R 6 into 6 sine 45, 6 cos 45, RC into 6 cos 45 minus 12 into 4 minus HC into 6 sine 45, 6 sine 45 is 0. So that is, so the RC is already known, okay. So RC value is 20.155. So 20.155 into 6 over root 2 minus 12 into 4, 48 minus HC is the unknown and 6 over root 2 is 0. So now 20.155 into 6 divided by root 2 is 85.510 minus 48, that is HC 6 over root 2 is equal to 37.51. So that into so HC you will be getting 8.841 kilonewton. So once you know HC, you can find HB is 8.485 minus HC. So 8.485 minus 8.841 is minus 0.356 kilonewton. So HA also equal to HB, that is minus 0.356 kilonewton. So we can find the reactions like this. So there will be a way to find the reactions. So once you have found the reactions, then approaching an inclined column or a beam is similar to approaching a beam that we have seen in the semester 1. So now if I take the element AB, so if we consider AB, so in AB we have now all the unknowns are known. So we have the (15 kilonewton, 10 kilonewton, and RA is 11.33, RB is RA is 13.33 and 11.67. 33, 11.67. This one is minus 0.356, minus 0.356. So this one, we know how to plot the shape of diagram, how to plot the variable diagram. Okay. The inclined column also same. Only thing is it's going to be in a different axis. Okay, it's going to be in a different axis. But everything, the procedure, how to plot it, sign convention, everything is going to be same. So now there is a way of plotting this diagram. I'll show you that the way that mentioned. Now in a beam, if it is hogging, if it is sagging, we draw on the positive side. If hogging, we draw on the negative side. Okay, but for the column, how to do it? So sign convention, two sign, when drawing the moment diagram, one of two sign convention is used in practice. The frame, in particular, if the frame is made of reinforced concrete, designers often draw the moment diagram positive on the tension side of the frame. In other words, if the moment produces tension on the outer surface of the frame, the moment diagram is drawn positive on the outer side. So if the frame is bending outward, then outer side will be in tension. So the moment diagram is drawn on the outer side. If the frame is bending inward, then the positive tension will be on the inner side, so the diagram is drawn on the inner side. That's one approach. So since concrete has a low tensile strength, it will be then possible to tell at a glance on which side of the frame the reinforcement must be placed. In this text, however, we will use the opposite sign convention and always draw the moment diagram positive on the compression side of the member. So in the book, all the examples, they would have drawn this on the compression side. So if it is buckling outward or bending outward, the bending moment diagram would have been drawn inside. Okay, so bending outward means when you take from the bottom support, if you take a section, it is like hogging, right? It is like hogging. So if it is bending outward means it's like hogging. If you take a beam, if it is bending upward means it's a hogging. So to be consistent with the beam method, so they are plotting on the compression side. So in the beam also, if it is sagging, we draw on the positive side. So it means that on the compression side we draw. Okay, on the beam. So to be consistent with that, they are using this method. So we will be adopting the same, which is convenient for us, because when it comes to beam on the when it is sagging, we draw on the positive side. So hogging, we draw on the negative side. Similarly, for a column also, if it is bending outward, we will draw it inside. If it is bending inside, we will draw outside. So we will be having a consistent approach on the drawing the bending moment diagram and shape. So now we will stop here, and when I see you on Thursday, we'll start from this point, and we'll do few more problems, and we'll complete this frame analysis. Then when we come back on next week, we'll start the new section. Okay, and I'll share you some more videos on the problems we have discussed for the other groups as well, so you can watch all of these and get familiar with that. So I'll try to avoid working out the same problem. I have noticed that I'm doing the same problem again and again, so which is no use, right? If I put it to somewhere to watch. So if I do different problems, then you can get different. So I'll try to do different problems this time, so you will have more examples to see. And in a overall, I find your batch to be very much better than the other group. So you keep hard working and then do that. Okay. So let us see. Again, we'll see this hole, right? Again, just something anywhere. Whatever the hole, we'll meet you on Thursday afternoon. Please ask those who can come to come in person, because the problem will not be solved anytime soon. So we'll continue. Uh, anyway, there will be COVID outbreaks. Things will. So as long as we'll try to go with the same spirit, we'll see. So we'll see. We'll again meet on Thursday afternoon. Thank you. Thank you everyone for joining online as well. Please come to the class.